Hello everyone, this is Kishan Singh and welcome to my week 5 project that is on verification of divergence theorem. So a quick overview. So first we'll define the our 3D body and parameterize it, and then we'll define a vector field on that body, and using that vector field we'll compute the divergence of the vector field, and then we'll verify the left hand side of the divergence theorem by hand, and we'll check it if we get the same thing from MATLAB. And then finally we'll verify the divergence theorem using MATLAB, that is we'll prove that left hand side and is equal to right hand side. So quick overview of the parameterization of the body. My body is an I section. So here is the only one parameterization of one part, that is the bottom flange, and the same thing can be done to the other two parts of the body too. So for defining the proving the divergence theorem, we need to define a vector field. So the vector field I've chosen here is a random vector field. The reason for doing that is just because we need to prove the divergence theorem. So I have chosen something that will not lead to unity or is zero, so that we can get a real value. So taking partial derivative of this vector field will give us the scalar field. The scalar field comes out to be 3x square plus 3y square plus 3z square, and this is the output obtained from the vector field. To obtain this output, the MATLAB should be coded in such a way, and this is the scalar field and this is the corresponding output. Now the main part of this project is to determine the left hand side of the vector divergence theorem by hand calculation. So what I have done here is taken the divergence of the vector field, that is the scalar field, and integrated it by applying the appropriate limits. So the first is the bottom flange. For this flange, the limits would be this distance, that is d by 2 minus tf. For the x, d by 2 minus tf going up till d by 2. So here is d by 2 minus tf going till d by 2. The other limit would be minus bf by 2 till bf by 2. Here is the other limit, and the last limit would be 0 to L, which can be imagined that it is coming out of the plane since it's a 3D body. And doing the appropriate integrals, we get the integral for the first part of the body as 5190. So second part, that is the top flange, would also be the same, just only one difference would be the limits would vary. Here is minus things, but since it's a symmetrical section, so the answer would be same. So here also we get 5190. The third part is the web of the I section, and for that also I have done the integral and applied the appropriate limits. For here only change would be the integral would be varying from minus t by w to t by w, and then applying the limits we get this as the integral for this part. Adding all, we get 14,889.375. Now let's check this if we get the same thing from MATLAB. So from MATLAB, coding this in such a manner, we get indeed the same value, and hence we have calculated it correctly. But now only partial part is done. Now the right hand side of the theorem should also be computed from MATLAB. So for that is nothing but vector field dot product with the normal vector times over the area, integral over the area. So here there are total 12 surfaces. So each of this thing should be done for each of the surface. So for surface 1, the normal vector would be pointing outwards, that would be positive E1, and similarly for each and every section. From this MATLAB we got it as 14,889. That is similar to that of we obtained from the MATLAB for the left hand side. So now I'll quickly show you the MATLAB code if it's running. So here's the MATLAB code. I'll run that. So yeah, from this we get indeed the values as similar, and hence our computation is correct. Thank you.